So today we're going to be finishing up what we did in 1.1 and then we're going to move to 1.2. In particular, let's just make sure that we understand how to do certain fractions. We dealt with compound fractions, we dealt with cross multiplying, all that stuff, but let's see if we can do a problem where finding the least common denominator is probably not beneficial to multiply your denominating terms out. So let's take the instance. This is still part of not factoring, I'm sorry. This is still part of fractions. But now let's take something like 5 over 36 plus, I don't know, 120 over, let's say 6. So already, you can choose to multiply the first term by 120 or the second term by 36 over 36. However, the numbers can get very big. So let's use least common denominator, or the other terminology is LCM, which stands for least common multiple. And the least common multiple states that you need to find the multiples of the denominators, 120 and 36, and then see where they have in common. So the multiples of 120 is 120, 240, 360, and 480. If I multiply by 2, if I multiply by 3, if I multiply by 4, etc. Now let's do 36. If I multiply 36 by 2, I get 72, and then I go to 108, and then afterwards is 144, and then we get to 180, and then we get to 216, and it keeps going. After 216, it gets to 252. If I add 36 to that, that's 288. And then it gets to 324. Then it gets to 360. Why did I stop at 360? Well, I'm trying to find what multiples they have in common. And it looks like the common multiple, the smallest one, is 360. I do not know how to get rid of this, but it might keep popping up. So the least common multiple is 60. That should be our least common denominator. So my goal is to have the denominator as 360. Now, what do I need to multiply this first term to get to 360? What do I need to multiply 36 to get to 360? Well, we did all this work. Why don't we just use what we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There were 10 multiples. So let's just say we can multiply this guy by 10 over 10. And how much multiples of 120 to get to 36? 360? Well, that's going to be exactly 3 times. 1, 2, 3. So now if I multiply them out, I get 50 plus 18. And if that's calculated, I get 68 over 360. Now, you can simplify this. So if you want to simplify it, go ahead. If you simplified it, both the numerator and denominator can be divisible by 4. So if I divide it out by 4, I get, what is that, 1, 20. Is it divisible by 4? I might be wrong. Let's see. I know it's divisible by 2, and I get 34 over 180. And I get 17 over 90. That is what happens when you simplify it fully. But that's how you deal with, least common or fractions with big denominators. And you don't really want to multiply them out like that. You want to just find the least common multiple to make your life easier. I don't want to multiply that 5 by 120. If the 5 was a 19, that would become horrendous. So now, we got to go to the next topic before we move on to section 1.2, and it is distance. How do we calculate distance in mathematics? If I asked you the question, how do you find a distance between 8 and 2? What would you tell me? 8 and 2. How do you find a distance between that? Or how do you find a distance between 8 and 2? You would say subtract 2 from 8, or 8 minus 2. Correct? Well, in mathematics, there are different alternatives, and I'm pretty sure somewhere along the lines when you were fighting distance, there's some point in your life where you did 2 minus 8 instead of 8 minus 2. Well, how do you fix that in the calculator? If you were using a calculator and you did 2 minus 8, you got negative 6. So what did you do instead? You turned it positive. It's still the same answer, it's just positive. So what we could do is introduce a terminology called the absolute value function. And what the absolute value function does is that it'll take anything inside the absolute value and it'll turn it positive. If the answer is already positive, it stays positive. However, if I did distance of 2 comma 8 and I get 2 minus 8, well, that's just negative 6. And the absolute value of negative 6 is positive 6. Now, in your book, you might see it as absolute value of any real number is going to be positive. And the other way you might see it is as the absolute value is equal to 2 conditions, or I guess an or statement. It depends on which one it satisfies. So if it's going to be positive, if A is already positive, it's going to be negative A if A was less than 0. And the reason why this is true is because if your A value was negative, let's take negative 3. Well, negative 3 follows the second part. Negative 3 is smaller than 0. So what they want me to do is do negative of negative 3. And a negative times a negative is a positive. So we get positive 3. That is the reason why the second condition makes sense. And that covers it for absolute value. Now we got to move into something a bit more complicated. We go into the next section of 1.2. And this is actually one of my favorite sections. Exponentials. So, first, we need a definition. So, x raised to some power, let's say 6. And for now, or not some power, I'm going to say a. Assume a right now is an integer. It could be a real number. It could be. But for our sakes, let's assume it's an integer. Well, any number with a subscript like this is called the exponent. And the x is called the base. Why do we call it base? It's because it's below your exponent. It's what's being raised to that power. It's what's having the exponent. This is the same thing as x times dot 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 times x a times. And that might not be obvious, so let's give an actual example. If I had 3 raised to the 4th power, that is just 3 times 3 times 3 times 3. Boom. That is what it means to be raised to the power of 4. So that's our first definition. We have this. Now we have some properties with that. I encourage you to try to figure out why these properties work, but with the interest of time, I'm not going to show that. Let's say we have x to the a, but I'm multiplying x to the b. What happens, this is called product of powers. What happens when you multiply two pieces, or two factors, but both factors have the same base? Notice this is an x and this is an x. What happens? If that is the case, you can actually rewrite this as x raised to the a plus b. You can actually add the exponent if the bases are the same. So example, if I did 2 raised to the 4th power times 2 to the 3rd power, that's simply 2 to the 7th power. I'm just adding it. No, this is for multiplication, not addition. If it's multiplication, I can add the exponent. That's property 1. Product of powers. Now we go to property 2. Power by power. So this is saying, hey, power by power is just exponent raised to another exponent. Product of power means multiplying exponents. Product means multiplying. So this time I have some x raised to some power, but this time I'm going to raise it to a power. I'm not multiplying it by another factor. I'm raising it to another exponent. And in doing so, all you have to know is that, hey, if I'm raising it to another power, that is the same as, hey, I'm going to multiply the exponents together, which will give me x raised to the AB power. So if I multiply factors with the same base, I add the exponent. If I raise an exponent to an exponent, I'm going to be multiplying the exponents out. I encourage you guys to try to figure out why this works. There are reasons why this works. Next, we have another one. Doesn't really have a name, but suppose we have a to the b, a times b raised to the c power. If everything is a single term, or if you're just multiplying, there's no addition, no subtraction at all, you can do this. You can separate the a to the c power times b to the c power, which is going to give you a to the c, b to the c. You can actually do that. And I apologize, I didn't give an example for this one, but let's just do a quick example. Let's do 4 raised to the second power raised to the 5th. That's just 4 raised to the 10th power. Now for this one right here, this is a good one. Let's suppose I have as an example 3 raised to the x power, or 3x cubed raised to the 4th power. Well, how do I calculate that? If we follow our definition, this is going to be 3 to the 4th power. Remember, a and b are placeholders, but this time 3 is not a placeholder. The placeholder for a is 3. So that's going to be 3 to the 4th power times x to the 12th power. Where did I get that 4 from? If you don't see an exponent next to it, there's always assumed to be a 1. Moving forward, now we can get into some special properties. In particular, one that I want to talk about is, let's see, we all know that a raised to the first power is a. I stated that earlier. But I want to figure out what a to the 0th power is. Now, if you look this up, or if a teacher told you this before, you figure it out, it's 1. Why is it 1 though? Why is any number raised to the 0th power 1? Well, let's take an example. 2 raised to the 5th power is the same as 2 times 2 times 2 times 2 times 2. Correct? You're multiplying 2 5 times. If I say 2 raised to the 6th, I just multiply an extra 2. But let's go backwards. What if I did 2 to the 4th power? If I went forward, I would multiply it by 2. If I go backwards, I have to do the inverse, which means I have to divide a 2 out from this guy right here. So that's just 2 times 2 times 2 times 2. It lost a 2. I divided a 2 out. Well, if we follow that same logic, if I had 2 to the 0th power, or I apologize, 2 to the 1st power, we know it's 2. If I divide that by 2, I should get 2 to the 0th power. Divide by 2 will give me 1. This is why I want you to treat it as integers for the exponent, because we can work with something raised to the 0th power. And I also say integers and not whole numbers because we can work with negative exponents. So what happens if I have 2 raised to the negative 1st power? Well, that's just simply 1 over 2. 1 divided by 2. We just keep dividing by 2. Do you see that? We're just doing the inverse operation continuously as we keep going down by 1 digit. Or, yeah, by 1 number. Then 2 to the negative 2nd power. That's just going to give me 1 raised. Well, 1/2 divided by 2. That's 1/4. However, it's easier to say 1/2 squared. Boom. And now, what you'll be realizing is that many of your assignments, if you're going to answer any problems, I want you to have no negative exponents. Do not leave solutions with negative exponents. Do not leave them with negative exponents. I want them positive. So if you have 2 raised to the negative second power, write that as 1/2 squared. If I have 2 to the negative third power, I want you to divide that again by 2, which is 1/2 cubed. I hope you're seeing a pattern here. I hope you're seeing a pattern. The pattern is, hey, any number to the negative b power, I can rewrite that as 1/a to the b power. That's a property you need. Any number raised to the negative power, I can just put a 1 over it and I'm good to go. Or a better way of saying that, I can just divide it out. I can divide out a raised to the positive b power. And this is very important. Why? What happens, hear me out, what happens if I have 6a to the negative b? Oh, now I have something multiplying that. Where does the 6 go? You might think it goes with the a. Could it be on top? Could it be sideways? Well, this is the same thing as saying 6 times a over negative b, which is going to give us 6 times 1/a to the negative b. And remember, 6 is technically 6/1. Technically, this is 6/1 times 1/a to the negative b, which will give us 6 raised to the a to the negative b. Do you see how the 6 stayed on top? What you're going to realize is that if the exponents, if it doesn't have a negative exponent, it'll go to the bottom. If it does have a positive exponent, it stays on top. And in this case, 6 is a positive exponent. It has an exponent of 1. So it stays on top. Now, another rule that we need to make is, hey, what happens if I have this? What if I have a fraction raised to a power? Let's say c. What happens if I have a fraction raised to the power? Well, that's the same as raising the numerator to that power and the denominator to that power. Boom. Simple. And then another thing you might be worried about is, hey, what if I have my negative exponent on the bottom? Because I said I don't want negatives, right? What if I have it on the bottom? Well, we still follow that same procedure in getting the inverse. However, I can't just put it at the bottom because it's already at the bottom. So instead, I'm going to move it to the top because that's the inverse. So it's going to be a raised to times b to the 4th power. All I did was move it to the top. Now, I could put a 1 over here. Technically, if I divided everything out or multiplied everything else and or cancel anything out, there's technically a 1 unless I'm adding. So that's why you could also leave it as over 1 or just by itself. That's perfectly fine. So I encourage you to try some problems in the book. You can definitely find some in the book. They have some very good ones. Look at your homework for those. But that is that is pretty much what exponents is all about.